So anytime you kind of run a calculation, you want to sanity check it, make sure that it's giving you something sensible. So we expect this density to be, positive somewhere, and definitely it should not be negative, and that expression certainly isn't. One thing to note is that for t, any negative time, the probability density better be zero, and that's almost by definition. The Brownian motion cannot hit some level b at time minus -5 or something like that, and so everywhere on the negative kind of part of that axis, we set the probability to zero. We've kind of picking up from the discussion that we had in the previous clip, sort of what does it look like? The density should look something along these lines. You can kind of think about again, like we discussed, what happens for the small t value. For small t, you have this. There should be a negative sign here. For small t, this gives very large negative values, which has exponential decay, which beats out this factor, and so you have a very sharp exponential decay around the origin, meaning that this time is not going to be concentrated near zero. So it's kind of telling you that the first time of the Brownian motion is going to hit, it's going to be kind of a little bit bounded away from zero almost. It's more likely that we wait a little bit of time before that event occurs, and then out at large values of t, for large time, that exponential factor is kind of non-existent. It basically is nearly 1, and the decay goes as 1 over square root of t to the third. So this is what's called a heavy tail distribution. A lot of the probability mass is allocated out to the tail, to long time horizons. And so we kind of see right away that we expect to get some fairly large time TB values. If we were to maybe simulate on the computer the outcomes of the random variable TB, we would typically see pretty large values just based on this observation that a lot of the mass resides in the tail. So the next sanity check would be, well, you have a probability density. It better, integrate out to 1. And so, this is why I've started this integral. This integral is the same one as the one from minus infinity to infinity. And here I'm just plugging in, the value. And a lot of these kind of look like they could be difficult to handle. And then, you just need a clever kind of substitution, clever change of variables to simplify things, as we'll do in a second. And here I'm looking at this, and you see in the exponent there's this awkward denominator, and you kind of want to get rid of this. So the obvious substitution is I want to make this maybe look normal. So we've seen these, how to handle a lot of these integrals that involve the normal density. And so I'm just going to set, cancel out the b squared, and with the numerator there, and put in my new variable of integration z squared to pop it back up, so that you get e to the minus z squared over 2. And then usually there are, always there are two kind of remaining concerns. One is to make sure that you change the differential, so the dt needs to change, and change the limits. And here I've also plugged in the bottom my square root of t cubed. So cubing this and taking the square root will drop the 2's, leave me the 3's, and flip things over. So z cubed will end up on top, and b cubed ends up on the bottom, and the remaining b is is up from here. So now dt dz is just this ratio. Here it's z to the minus 2, take a derivative. That's how you get the minus 2 that comes down, and minus 2 minus 1 is 3, so this pops in the denominator. And that's, I guess, what I have there, right? Yeah, so I've just plugged in the differential right here. And so now you kind of watch the cancellations go, right? The z cubed cancels, the b cancels entirely, so everything sort of falls into place nicely. All that kind of stands in the right, all it remains is a 2 here, and everything is exactly this way. The limits of integration are flipped here, so you see why did I flip them even back there. So to get, when t is infinity, what's the only way to get that? That's making z equals 0. That explains the top limit. And what's the only way to get t equals 0? That's taking z out to infinity. That explains the bottom limit. And then if you flip the limits of integration, you have to switch the minus sign. So that's how we get rid of the minus sign, which would have been not great for if we were talking about probabilities. So I mean, that basically wraps up the calculation. You have a nice integral over a standard normal density taken twice, and it's from 0 to infinity. So the Gaussian density is symmetric about the origin, and so we've integrated half of it here, giving us a half, and then multiplying by 2 gives us 1. So that's a check. And so now at least if we've done all the work right, hopefully this is, well, and it is the probability density of that time, and it definitely is a probability density of some kind. It's non-negative, and it's integrates out to 1. So the final thing is we saw these heavy tails happening here. So we expect very large values for t to occur if we were to actually simulate this on a computer, or watch some maybe process that in the real world behaves like a Brownian motion. And so I want to kind of raise the question of whether this whether this random time can actually be infinite with any kind of positive probability. And the answer to this comes from kind of, this is the standard way of showing this of showing whether this is true or not. So one thing you can kind of observe is that, what does it mean for a random variable to be equal to infinity? Well, it means that TB is equal to infinity if it's greater than every single natural number. And so here I've written, this is the intersection over all events of this form. So this is saying TB is greater than n. So I just picked a natural number, doesn't matter what it is. You can pick 0, 1, 2, 3, this will work for all of them. The definition of infinity is that infinity must be greater than n, must be greater than n plus 1, must be greater than n plus 2, must be greater than n plus 3, and so on and so forth for all natural numbers k. So this is an intersection over all of these events. And now I can take a probability around this set. So now I have an infinite intersection here, which may seem weird, but that's exactly what you would require to define infinity. Infinity is defined as something greater than every single natural number, or real number, doesn't really matter. And what is this bounded above by? This is bounded above by the largest set in this intersection, which is if I'm starting my count at n, let's say n equals 5, then it would be greater than the probability that TB is greater than 5. And this is true for any finite number n, for any natural number n, this is true. And so I've just developed this upper bound for absolutely every single natural number. So now, as long as I can get this calculation, as long as I can understand what what this probability looks like, I'll be able to conclude what the probability of TB being infinite is. So here I'm running that calculation. This is directly by definition. The probability of exceeding n is 1 minus the CDF at n. Our expression for CDF was this complicated thing. It was 2 times the probability that the Brownian motion at time t was equal to n. So it had this form in terms of the normal CDF. And now here I'm just kind of simplifying things a bit. I get a cancellation of 2 with this guy here, and now this, now I have exactly what I need. I have an upper bound on the probability that TB is infinite in terms of this probability that it exceeds n. And we see that if you take n larger and larger, this is true for any value n. If you take this to be larger and larger and larger, what do you get? What does this value here approach? It approaches 0. What is phi of 0? Phi of 0 is the probability that a normal at mean 0 is greater than 0, which is 1/2. And so this whole expression, 2 times 1/2 is 1, minus 1 is 0. So we are approaching a probability of 0 as n becomes larger and larger and larger. And that's exactly what you have here. You have that the probability that t is infinite is bounded above by this for any integer n. So now take n to be, take the limit as n goes to infinity on both sides. Take the limit as n goes to infinity here. There is no n, so this leaves it on the left side unchanged. And take the limit as n goes to infinity here, and you'll get 0. So in the end, the final conclusion is that t b is infinite, is less than or equal to 0, and therefore is equal to 0 because it cannot be negative. So in the end, we have this is equal to 0, or in other words, the probability that TB is finite is equal to 1. So while this time will typically have very large values, it is still a finite random variable. We should not be expecting the Brownian motion to kind of never hit this thing, although expecting is a bit of a catchy word, which I'll talk about in a second. So the random variable, or the realization of this random variable, is indeed finite, as we just argued. So this is a little bit technical, but it gives you an idea of how to carry out these proofs. And finally, I just spoke about expectation. You can kind of see, when you start computing expectations against that density, you can kind of see how you can quickly accumulate too much probability in the tail here to have infinite expectations. So one thing that we know is that the integral from any number, so you can, c is just any fixed number here, any fixed constant. If you integrate out from c to infinity, the 1 over t to the p raised to some power, this will either converge or diverge depending on what p is, and it diverges when p is between 0 and 1. And so you can start kind of using this fact. You can kind of see when expectations of this time are actually infinite, and in fact this is pretty much immediate as an implication. The expected time of the Brownian motion hitting B is actually infinite. It is a finite random variable, but it has an infinite expectation. And we've seen examples of this before with Markov chains. So we see it again here.